Hi friends, I am doing the Termpaper on the topic transmission line and a coaxial cable. So this is the outline of this presentation. There will be an introduction and we will briefly discuss the theory, then we will look on coaxial cable and its losses, then conclusion, that's all. Now, what is a transmission line? Transmission line is a specialized cable or any other structure designed to conduct electromagnetic signals via a bound channel. So, in a transmission line, there will be two conductors. One is to transmit the current from source to the load, and another is to transmit back the current from load to source. So there will be two connections. That is to complete this circuit. Now, what are the examples of transmission lines? One example is coaxial cable. Another example is circuit. We use in circuit boards. There will be circuit boards and there will be connections in that circuit. Sometimes we call the waveguides and optical fibers as transmission lines, but actually in this case we do not consider them as a transmission line because its mechanism is different than this transmission line. So here we do not consider waveguides or optical fibers as transmission lines. And now we use the transmission lines as connecting radio transmitters and receivers, distributing cable or TV signals and computer network connections, and in laboratory applications, and there are many other applications for a transmission line. And another application is the wiring in our houses, but that is another case. We do not include that here. Here we are looking only for the signal transmission lines. Now, why do we use transmission line theory? Why not we use Ohm's law, some such laws to explain these things? One of major thing is the wavelength of signal that we handle through a transmission line. Means in labs are very high signals. Means in the frequency is in microwave range, radio wave range kind of things. So that is the wavelength of that signal is much lesser than the dimension of the length of this wire. That's where then we cannot directly use Ohm's law or any other laws directly here. Here the signal is traveling almost same as a traveling wave in a free space. So this signal also shows the phenomena like transmission, reflection kind of things. We cannot explain that things using the Ohm's law or such other such laws. Then we should use transmission line theory here. In our household wiring, the frequency is in India it is 50 Hz, in America it is 60 Hz, whatever. It is in the its wavelength is in the order of 10 raised to 6, which is about the radius of Earth. That is much lesser, greater than the length of our wiring, even length of our household wiring. So we do not have to use transmission line theory there. But here our signals are in millimeter or centimeter range, so we should use that here. Now, we are modeling this transmission line as with an equivalent circuit. In this equivalent circuit, there will be an inductor, there will be a capacitor, there will be two resistors. Let's see what is the need of these things. See, the conductor we are using is not infinitesimally small. It has a finite width, and the current is passing through it. Then there will be a magnetic field around that, and the signal in this, the current in this conductor is oscillating in time. That means this magnetic field is also oscillating in time. That will create a back EMF in this, back EMF or EMF in the other conductor or whatever. There will be an inductance effect. So we use this inductor to represent that phenomenon. And we already seen that in a transmission line there will be two conductors, not only one conductor. And there will be a capacitance effect between these things. We already seen that there will be changing magnetic field, and there can be electric field also, and the current in this both conductors are changing. That means changing magnetic field is there, that will give rise to changing electric field, that will leads to a displacement current. So that this conductor stands for that phenomenon. That is exactly a capacitive effect. This capacitor stands for that thing. Now, what is this resistor means? See, our conductor have an inbuilt resistance. So this resistance R stands for this, and this resistor. What is this resistor? And I represented that by the letter G. See, there will be an insulator between both of these lines, but that dielectric may not be an ideal dielectric. There will be a small conductance on this dielectric. That means some current will be lost to this conductor, so this dielectric. So this G stands for that thing. So this is the equivalent circuit of a transmission line. Here our L, R, C, etc. All of these etc. I take for unit length. See, this L is for inductance per unit length, and R for resistance per unit length, kind of things. And this right side is plus Z direction, left side is minus Z direction, and this length distance is taken as delta Z, and this resistance is the resistance effect of these things. Actually it is a small portion of our transmission line, but here to model this I take like this. Now from this equivalent circuit, by using KVL and KCL, we write these equations. We write this by using Kirchhoff voltage law and write this by Kirchhoff current law. Now when we rearrange this, see, we can cancel this thing, then there will be delta Z in all cases. There will be an Z here, this will cancel out, then we will get this equation. Now there will be I plus I of Z plus delta Z. This can be right here, then there will be delta Z in all other cases, then that will be minus of I Z plus delta Z T minus I of Z T divided by delta Z. When we take the limit Z delta Z tends to 0, that is a derivative. So that we get here. Now we got two coupled partial differential equations. By decoupling it, we will get like these two equations. Now for our easiness, we are taking this as complex numbers. This small v is the real part of this capital V of Z e raised to j omega t, and the small I is real part of I of Z e raised to j omega t. Now we substitute that for our decoupled differential or coupled differential equation, whatever it is, we will get like this. Now the general solution will be we will get like this. We will get the general solution for both current and voltage. See, there will be V plus V minus and I plus I minus. V plus stands for the wave traveling in plus Z direction, and V minus stands for the wave traveling to minus Z direction, means coming back. Similarly for I stands for plus Z direction, minus I stands for minus Z direction. And I had introduced a new quantity gamma here. This gamma is actually a complex number, so we can write it like this. Physically, this alpha means the attenuation constant and beta stands for the phase constant. You can see that when we write like this, alpha e raised to minus I j beta, and this will be an oscillatory time, and this will create a profile like this. That means the amplitude of the traveling signal is decreasing when, if we go in positive Z direction. Similarly, in coming back, the amplitude is decreasing like this. That means when the wave is coming back, its amplitude is changing, decreasing. That stands here. Sorry, our graph should be like this. So that stands for alpha. Now, in our coupled differential equation, now substitute j omega instead of delta t. Then here should be a v. Then we will get the equations like this. Now I introduce this quantity z, that is for r plus j omega l, and y is g plus j omega c. Now our gamma will be square root of z times y, and that is same as alpha times a beta. Now we are introducing the quantity characteristic impedance. This is the ratio of z, square root of ratio of z and y. That can be written as like this. This characteristic impedance is the impedance inbuilt to every transmission line. Even there is no resistance, there will be a characteristic impedance to the transmission line. That is, physically we can say that it is the ratio of the wave traveling in positive, ratio of voltage and current traveling in positive Z direction. So that is the characteristic impedance. This we already see these things. I already told that the amplitude of voltage and current will decrease according to plus Z direction. If we treat it as very large frequencies, this R will much lesser than omega L, and G will much lesser than omega C. Then we will get the condition, we will get the phase velocity of the signal like this. That is 1 by root L C. This is familiar to us. Now we see that these electrical signals are traveling same as traveling wave. When the wave meet an interface, some of it will get transmitted and some of it will get reflected. Here also we can see similar kind of phenomenon. See, if we meet a load resistance, here we are taking a load resistance, the waves will get reflected. Waves will come here and go back. This is same as reflection. There is a ZL and Z0. There can be the line beyond this point, then the wave get transmitted. So some wave get reflected, some will get transmitted. In practical, this can happen in every point of a line. That means in every point some waves will get reflected and some waves will get transmitted. This can happen in every point. Now, if Z low equals Z0, the reflection coefficient will become 0. That means no waves will get reflected. All waves are get transmitted. This condition is called impedance matching. So by matching the impedance, the whole power will get transmitted to the load. All power means all power from the transmission line will get transmitted to the load resistance, that is impedance matching. Now if this condition, what happens if this condition is not satisfied? Then that will lead to a loss. Actually we are not getting the sufficient signal, that is actually a loss. Then that is called return loss, and quantitatively we can write that as the 20 times of logarithm of reflection coefficient, and it is written in decibel. Now let us look on coaxial cable. The structure of coaxial cable is like there will be a conductor at the center, and around that there will be a dielectric insulator, around that conductor again a conductor, and there will be an insulation. This is the basic structure of a coaxial cable. See, this is exactly same as I showed earlier, and the diameter of central conductor is D, and inner radius of outer conductor is capital D. This is the construction of the coaxial cable. Now we already saw there will be inductance and capacitance for a transmission line. In here we are particularly calculating the capacitance and inductance of coaxial cable. This we can found by just using the Ampere's law or whatever it is, Gauss's law kind of things. There will be a central conductor, there will be an outer conductor, and the current is passing through it. There will be a magnetic field around this. Then now consider a strip here. Find the magnetic flux through that strip. Then we can use the formula epsilon equals L d I by dt. From that we can find the inductance. To find the capacitance we can use the same trick. Consider the structure like this. Charge the central conductor. Now find the potential between both this. Now compare with the formula Q equals CV. Then we can find the capacitance. Now, what are the major losses in a coaxial cable? First thing is resistive loss. This is coming from the material properties. There will be an inbuilt resistivity to the materials which is used to make this coaxial cable. So resistive loss is coming from that. Next thing is dielectric loss. I already told that there will be a conductance for this dielectric, and there will be a capacitance effect. This capacitance also depends on this dielectric material. So this loss is coming from that, but it is lesser than this resistive loss. Third one is radiative loss. This is happened by the radiating of signal, means electromagnetic waves in the coaxial cable. Another thing is loss over time. This happens because of aging of the coaxial cable materials, means maybe dielectric, maybe because of rusting of material, kind of things, maybe because of oxidation, and there will be a different reason for that. So that are the major losses that we are looking in coaxial cable. Also we already saw the loss because of reflection earlier, and someone did an experiment to find the characteristic impedance and attenuation etc. of a coaxial cable. They did for 3 materials. Here I cannot read that. So but we can see the graph. In the first plot we can see the plot frequency versus Z0. In second plot Z0 versus attenuation. Here we can see that higher the frequency, the Z0 is decreasing. Here we can see that higher the Z0 characteristic impedance, lower the attenuation. That means frequency high, attenuation is high. attenuation is increasing with the frequency that we can see here. Now, this observation was done by this person. This observation is done in 3 materials. We can see the plot of each, and there is an application for this. We see that this attenuation is depending on the material which is filled in, dielectric material which is filled in between the coaxial cable. Now, if we fill some other liquid or gas or whatever, maybe sometimes we can use the solid, we can use this phenomena to find the material properties of that dielectric material by using a special kind of coaxial cable which we can fill the dielectric material. So we can use this property. Now let's move on to the conclusion. In this presentation we have seen the need of transmission line theory, differential equation and its solution, and major phenomena like reflection and transmission, and the major properties of coaxial cable, and different kinds of losses in coaxial cable, and it's one of its application. Now I am concluding my presentation here. I thanks to Professor Basudaya Dasgupta and Krishnendu Maji, who is our reader, and especially to Dr. Paulbert Thomas. He is working as a professor in Cochin College in Ernakulam district, Kerala, and definitely to you guys who listen to my presentation. Thank you.